Hello, hello, hello. Jetzt. Hi. Yeah, I hope it's okay for everybody. I do it in English. It was in the program in German. Okay, no complaints. Fantastic. That already worked. Yeah, so welcome to my presentation. I'm talking about systematic heat recovery with pinch analysis. We do this a lot since 3 years in the pharmaceutical sector. Shortly about our company. We're a small engineering office based in Karlsruhe, Germany. We basically do product development and consulting and also some special plant constructions. Our goal is to change the industry to sustainability, which we defined as efficient, long-lasting, and only natural refrigerants. Would be sooner or later only natural materials, but that's too early now. So there is some regulations on this topic we are talking about in a second. I want to start with these regulations first. Yeah. So I think most of you are familiar with the new F-gas regulation that was just enforced, or new is it's not, it's from some years old, but it got enforced like it was planned back 2009. And that hit some of our customer very surprisingly, even it's a very old law. Yeah. And then on the horizon, there is the restriction from the ECHA. ECHA is the highest chemical authority in Europe. They bring out the REACH. Some of you might familiar with cancer-causing substances with the REACH. So usually you have to do a REACH report in your company. And basically they think about to ban all PFAS. And at the moment, this is in the draft state, which is already commented, and we will see how it leaks. We think it will be enforced in 2027 for refrigerant, but this is thinking, this is Glaskugel. Yeah. The next thing hits us in Germany already. What is for us wonderful is the energy efficiency law, but it's from a European directive, so it will hit sooner or later at least the other Europeans members in this audience. It basically says you have to recover your waste heat and you have to give all your information on the waste heat you bring into the ambient. Okay. So before we start a bit more in detail, I have two fun slides and then we go to the scientific part. But we figured out, talking with a lot of experts in the industry, that usually it's worth to talk a bit about beer energy. If this is the only takeaway from this presentation, it's also fine for me. So basically what you see here is beer from my hometown. Yeah. If there's a warm summer day, this beer is warm and you put it into your refrigerator. The refrigerator does something wonderful and it takes the energy from the beer. Yeah, we call it beer energy. And with some electrical power and a refrigeration machine or heat pump, it brings it to the kitchen and heats your kitchen. And the beauty of it is that the beer energy is bigger than the electrical power. So with some electrical power, you get a lot of heat. Yeah, and basically, this ratio is called COP, and a good coefficient of performance on a good domestic heat pump, you have a ratio between 4 or 5. That means with 1 kilowatt hour of electrical energy, you can have 5 kilowatt hour of heat, and that's 5 times better than the electrical heater and other technologies. We come to this point, beer energy, later again. So what we find state of the art, this is the brewery that brew our wonderful beer where we have the beer energy form. And also in the production process, they have a lot of waste heat, which they bring over a chiller, you see here on the picture, to the ambient. And this chiller is also able to get the heat away in summertime. So basically this means it at least has to be able to do 40 to 50 degrees condensing. Otherwise you get not away the heat in summertime. And next to it, there is a famous accelerator, Cyber Lab. There's 300 young people working on the future of this at our country, yeah, and they burn a lot of gas to not freezing in wintertime. And I think that's the dilemma, what we see already. There would be an easy solution to just recover the energy, especially this is already a water refrigeration machine that can directly give the heat to the other building. Okay, so how do we solve this dilemma? We have a systematic approach for it. So basically, there's already the points written. This is more for the handout, so we go in detail into the point. The first thing we do, and that's usually I recommend our customer always to do on themselves, is basically get their gas bill and look how much gas they burned over the year. And in a good way, they have it by month. So you get basically here the kilowatt hours and you get the burned gas. And this is the curve over the year how much this customer of us burns. So we are allowed to show you this. It's neutralized. And the other curve you see is basically how much beer energy he gets from his chiller system. This is also easy to find. You just check the power you put into your refrigeration equipment, and in a very rough estimation, you take a COP, which a normal expert can give you very easy as an estimation, and then you see, okay, this is my waste heat. And the surface below both lines is your maximum potential, what you can save in your whole factory. Okay, so here the bad news is in January and December, we are not able to get enough heat out of our refrigeration system. But the good news is 10 of 12 months, we can completely get rid of gas. So that's the first start. So this surface, you multiply with your gas price, and then you have a financial potential. Okay? And usually on our customers, we get some millions out of this per year, what they spend on gas. Yeah, and then we tell them, okay, if you spend some million on gas, we see we can reduce 80%. We should talk about how we can do this systematic. And that's the next slide. So basically what we do is a pinch analysis. Pinch analysis is a very scientific method, very detailed, to compare different heat source, heat sinks, and get also some more data on heat exchange and other things. We simplified this method a lot, which helps to find the perfect solution. Because what we do is basically we do a diagram where we put the temperature over the kilowatts. And then we take the different heat sources. So this customer, for example, has a cold brine where he collects heat from his factory for all the processes that need cold brine. And he has cold water in his factory where he collects all the heat from other processes. So we have, this is our beer energy, okay? And on the other hand, we have heat sinks. So for example, heating from modern buildings, 45, 50 degrees. We have some older buildings, we have hot water, we have process heat for different processes, we have steam and other things. That's everything he needs heat. That's very simplified. The real diagrams look a bit more complex, okay, but not too much. And then we usually divide it between winter and summer. Sometimes we even look into the seasons between winter and summer, and there is also some specialties, but this is too much for this presentation. Okay, so basically you get here this diagram, and then you can already see in this example, in winter time, we are able to do with the waste heat from these two systems, plus the power. This is the beer energy, you remember, we get the electrical power, we can nearly do the complete hot water and heating of the complete factory. And in summertime, we would be even able to do the complete steam out of the waste heat. We come to this in a second. Okay, the next tricky thing is, especially in pharmaceutical industry, there is not like all continuous processes. So we have a lot of processes that are batch processes. To very much simplify it, and don't be mad with this easy example, but I like to describe it, especially in young engineers, with flushing a toilet. So once in a day, you have a need of a batch process sitting on the toilet, okay? And this you want to flush away. So either to have this away, you can make a very big pipe with a very big pump and give a lot of power to it, or you have this box in back a wall with a small water pipe that fills over 2 minutes and then gives a fast flush. And basically we have this a lot in the industry. So this is called batch process. So at a very short time, you see this process, this is a real process, has 300 kilowatts for maybe, this is hours, maybe 2 hours, and the rest of the time it maybe is between 50 and 100 kilowatts. So could you imagine we now feed with this process, cooling demand, we feed a building, So we could, this is on Monday, so on Monday we could heat up the building on 70 degrees. Everybody likes a sauna, and end of the week they would have 15 degrees in the building because there's not enough heat coming, I think that's a pretty bad idea, So basically what you need to do, like in the gearbox, you have to synchronize the processes to each other. So you have to look on specific availabilities of heat, and a very easy example on this would be, we do a small heat pump. This small heat pump permanently heats the houses, and it generates ice. So we have a big ice tank on Monday morning, and when the big demand on cooling comes, we melt the ice. So we need a very small chiller or heat pump. Yeah, we have an ice tank, and we can recover the complete heat. Yeah, and this is an easy example. Reality is a bit more complex, but we come to this in a second. Okay. The next thing I want to show you, and that's one of my favorite diagrams in refrigeration industry. And if you understand this, you know a lot more than I think most of the people. This is coefficient of performance. We had this ratio, beer energy, if you remember, to electrical power. And this is the Carnot. Carnot is the best possible process for constant temperature. You cannot get better than this. This is just physics. You can Google it if you don't believe me, okay? So basically, you see it's a nearly quadratic function. So basically, this is now on ambient temperature fixed 20 degrees. So we hold the ambient temperature, okay? And the higher you go with your heat pump, the lower the possible COP. And a very good rule of thumb is if you have an efficient heat pump, you have half of this COP. So make the example. We have a house. We want to have 40 degrees. With 20 degrees ambient, we could get in a perfect world where we have unicorns, a COP of 16. That means with 1 electrical kilowatt, you get 16 heat. Not possible. But we know we can do 8. What is fantastic, okay? But if we go from 20 to 60, we can do 8 in perfect world, 4 in real world. And I think you see the problem, yeah? So if we go, the higher the delta T we go, the smaller the possible COP and so smaller the real COP, because that's physics, okay? It's the other way around on refrigeration, but this is another topic for another time. That's also one of my favorite topics. Basically, if you look at at your heat pump and your heat pump project, the most important thing is that the COP you can reach with your heat pump is a ratio to the you pay for electricity to gas. This ratio is, in Germany at least, most of the time free. So if you do a beautiful heat pump with free and you think you have done it for environmental reasons and your management looks at the number and there is no amortization, they don't like you anymore. So you should keep this in mind, okay? Good. So basically with this in mind, how we do this approach. So basically we look for the low-hanging fruits. At least if the customers, we have in pharmaceutical industry 2 kinds of customers. One kind says there's energy efficiency law, I have to do something, please show me the low-hanging fruits. If we go to low-hanging fruits, obviously, like we discussed, our chiller already can do in general 40 to 50 degrees. So why should you the hell buy a heat pump? You have it already in your factory, you can directly use it. I show you in a second, okay? And if you have still a lot of heat available and in the pinch analysis you see it's fitting to other processes, you can get from this heat to this heat, also with a COP around 4, 5, 6. It depends a bit on the delta, like you just learned, yeah? The 90 degrees. 90 is the industry standard. If you go to any booth in the whole 7A, you will find heat pumps that easily can do this. At the moment, they are more in the direction of 125 degrees. That's at the moment the new gold standard. The old was the 90 degrees. That's easy to do. And if you still have, like we saw in summertime on the other customer, and that's the other kind of customers, they want to be energy neutral. That's another goal than having most efficient amortization, yeah? Then they can do also steam, like we see in another project in a second, okay? Let me check the time. We're good in time. Fantastic. So if you have your standard cold water chiller installed, so these are 2 chillers, you see, they produce 6, 12 cold water, yeah? This is the blue lines and get 12 back. And forget this, I explained this in a second. Usually if they are the kind that they have a dry cooler on the roof or a cooling tower on the roof, they have a water-water connection. And on this water side, they have a Kondensationshochhaltung, what is in English? They have to have a higher temperature also in winter time to have a good profile on the chiller. Yeah, so they can got not unlimited down with the condensation. Yeah, so usually they have already this freeway valve, they have already this pump. And we crazy guys, we just installed here a heat exchanger. Yeah, so now we can heat up this loop also in winter time to the 40, 45, 50 degrees, and we can bring it in directly into the heating grid. This invest is around with everything, and also you make your plant construction company happy, maybe 30,000 euro. In most projects, this is a return on invest below 1 year. Okay? And also, if you have several chillers, you can still, if your heat demand is lower than your cooling demand, you can run one on heat and one, because you just learned the COP from me, yeah, or you knew it before, I guess, that you can still run this on only cooling with 20 degrees. You can run this on heating 50 degrees. And with this, you can easily control your heat, because everything you need at heat, you bring in the grid. Everything you don't need at heat, you bring on your dry cooler. Very simple, okay? So you can control with a standard refrigeration machine, 6, 12, and 50. Everybody happy, okay? Happy customers. Okay, so smart talking, real project. One of our customers has a standard chiller, water, like I explained to, dry coolers, and today he's burning gas. He has several buildings, 90 to 55 degrees. That's how he run. Last year, we did measurements in wintertime and looked for each buildings. He has several buildings, which temperature the building really needs. So basically, we reduce the temperature for each building and see if it's still running. Everybody happy? Yes, everybody happy. So we figured out he has buildings that can run 55, 45. So basically what we did is this famous heat exchanger I just showed you, and this building is directly running without any additional invest of a heat pump. But he still has a lot of heat available, so we decided to make an extra heat pump, and we figured out that the 90 degrees is not necessary at all. All his processes, what he needs is 75. So basically this heat pump has a very nice COP, because it only goes from 55 to 75. That's a piece of cake for a heat pump, okay? You remember the graph, the 20, yeah? So Unicore land, it would be a 16, but that's not working. Okay, so this is an example. Another example, this is a general slide, what you can do. So if you do your analysis, you see you have a process waste heat. So we have a lot of customers, for example, that have water treatment going to the plant with 50, 70 degrees. We have one customer, the road doesn't freeze from the water treatment plant to the factory of this customer. The street doesn't freeze in winter. Even there's snow everywhere, this street is empty of snow because it has 70 degrees wastewater. Yeah. So basically you can take obviously this heat out, yeah, and also like we just learned, have buffer systems, and like I described, many other solutions. I have to make it quick. I want to show you this. We don't have, yeah, okay, we have the time. I do it fast, yeah. This basically is one solution to do steam production, yeah. This is a very established Brüden compressor, steam compressor from chemical industry. They are used since 30 years in the industry, thousands of machines in the field. They are used to recompress steam, but recompressing steam you also can do in a heat pump. So this is a project we do at the moment. We have a customer doing sterilization. So basically he's cooking something. He has 100 degrees waste heat, yeah, and he needs 150 degree. Yeah, so if you remember, the diagram is 50 degrees, so we can do a COP of 5 for 150 degrees steam, because the delta is low. We don't take ambient. We have the beer energy already on 100 degrees, yeah. And with this project, basically, we can cook the condensate from the process back and recompress and have our 150 degrees again, yeah. And that is not all fiction, what I'm telling. This is not a project we are involved. I'm very clear disclaimer on this, but I'm very thankful to Takeda that I'm allowed to show you this, okay? They do this already. So at the moment, they have their centralized refrigeration system for their factory in Vienna, yeah. They have a heat pump on it where they do already 70 degrees today, and they just started to build now an extra heat pump for doing 70 to 134 degrees. Yeah, it's from SPH. Yeah, and then they do with this pillar machine, they do the steam production 184 degrees. But they, as I mentioned, they have the goal to be climate neutral. It's not about amortization. Okay, if you have questions on that, I saw that Harald is here from Takeda. He's usually on the booth of the historical refrigeration guys, yeah, in Hall 9. Okay, so very nice project. So I'm out of time, so I'm thanking you for listening, and if somebody has questions, I'm happy to answer. Thank you very much.